Hello everyone, I hope you can hear me well. My name is Teon Banek, also pronounced as Teon, a bit like that character from Game of Thrones, but I have no relation with them, so don't mistake me. The topic of this talk is the life of a query in a distributed graph database. And I'll start off by introducing myself a bit more. Basically, I graduated from University of Zagreb, Faculty of Electrical Engineering and Computing, majoring on computer science. Besides programming, I also enjoy fencing, as of recently, lasagne and black tea. Also, maybe I shouldn't mention this in public, but I like a good glass of very good whiskey. So, yeah. I'm working currently at Memgraph as a lead developer on Query Engine. And I'll be talking about that today. So a bit about Memgraph. We're a small startup founded in 2016. We are building a graph database. And our primary goals are that the graph database is in memory. And this allows us to exploit it for high-performance analytics, queries, or similar. And as of recently, we also support distributed deployment so that you can have a graph stored across multiple machines and run queries there. You can find out more about us on this website. So we can begin the presentation proper. First, I'll explain a bit about graph databases and the OpenCipher query language, which is used to query such a database. Has anyone heard of OpenCipher? Maybe show of hands. Oh, yeah. Okay, excellent. I will explain how we parse it, then perform semantic analysis, and the meaty part is query planning and optimization. Finally, we will show the execution on an example. Let's start off with an SQL query, which walks into a bar, sees two tables, and asks them, "May I join you?" Well, what happens next is usually something like this: a large SQL query, which performs multiple joins, and if we do a lot of joins, it becomes very unreadable very quickly. But why do we do this? We want to find out a relation between some data. And this is quite useful, but it models very nicely in graph databases. Basically, we store the relations as edges in a graph, and we query that. But to simplify things, graph database use a different kind of language. In our case, we are implementing OpenCipher. And OpenCipher example can be seen at the top. It's kind of similar to SQL, but a bit different. For starters, we have a match clause at the top, which will perform a pattern match of the subgraph we want to find in our whole database. And the pattern is displayed as an ASCII art-like of a node edge to another node. So node is in parentheses. Here we want to find node labeled captain and store it in variable A. Such node also needs to have a property name with value Kirk. In our case, we are storing actually a property graph. So each graph element may have multiple properties. And then we expand across outbound edges which have the type friend of into a destination called B. So in our case, we would like to go from Kirk, the captain, to friends, which are McCoy, Spock, and Uhura. But also, we have a filter in where clause, which says that the destination needs to be an officer. In this case, we would filter out doctor and only display Spock and Uhura. But the results are not the whole nodes, because we have a return, which aliases an expression b.name, which is just a property access, to get only names of those nodes, not all of the properties. I hope that's clear. So we can begin with parsing. So for parsing, we are using Antler4. It's a parser generator toolkit, which reads a file which contains a Backus-Neuer form-like grammar description. And it produces in the target language the parser for such grammar and also the AST data structures. In our case, we are targeting C++, so that's what we will get. But unfortunately, that AST which is produced isn't very readable and usable because it contains all of the productions in the language, which aren't really necessary when working on it. So we translate that AST to our custom, a bit more higher level. And this has also two additional benefits. So we can replace maybe Antler with something else and just replace this pipeline stage with our own custom parser, which produces the desired AST. Also, we can support other languages which may have semantics similar to OpenCipher, so we can map it to the AST. And after that, we will strip out all of the literals and parameters in the query. This allows us to have a uniform structure of a query and use it to hash the query, store it in a map, which will be used as a cache. So afterwards, if a similar query with just different values appears, we can reuse the already parsed AST and skip the whole parsing process. This is especially useful with automated scripts which perform a couple of same queries on the database a lot of times, which is most use cases when you have like an application talking to the backend and the user only has available some features. So next up is semantic analysis. Basically, here we perform various sanity checks, which is like whether the user is trying to create the same element multiple times, so we will raise an error. Similarly, with combining clauses which aren't compatible, like union and union all. We also detect other various errors which haven't been detected before, like trying to create multiple same keys in the same map. But most importantly, we generate symbols for variables. And this is basically validating the scope and bindings of variables, which needs to be done in all programming languages. So the user knows whether he's using something which is out of scope, or perhaps shadowed, not bound, or similar. And we perform rudimentary type mismatch checking by having some very basic type deduction. Let's take a closer look at symbol generation. So we basically want to map each variable to a value. But the values will be stored on a frame, which is a simple data structure, essentially an array. And you can think of it like a stack frame. Basically, we reserve all the needed places on the frame for each variable, and the values will be stored there. And symbol is used to look up into that array to find the desired value. It's a good thing that OpenCipher doesn't have dynamic allocation keyboards clauses, so we can pre-allocate the whole stack frame for the whole execution. And we will see how that is done a bit later and used. So let's take a look at our example. First, we will start off with the first variable a, which will store our nodes we find. And it gets first place in the frame. And initially, the value is null. It's empty. Then we will do the same for node b. But what may not be obvious is that we also have an edge, and we need to store the value for that edge also. It's not named, so we would give it an anonymous name. This is done in compiler stage parsing. Afterwards, we also have the alias b, which is different than the destination node, so it needs to have another position in the frame. So we are done with that and can continue with planning the steps of work. So the steps of work are usually called logical operators, similar to how you would do with an SQL, but they aren't based on relational algebra, which is kind of unfortunate. We will have different ones. In our case, we will perform a pattern match. So initially, we want to find the source node, which will be done with scan all operation. Now, since we are talking in a distributed context, scan all will actually look up all the nodes in the machine that is executing that scan all. So in a distributed cluster, we have worker machines which store parts of the graph. And each one will perform scan all in parallel, producing the nodes on their machine. The next one is expand, because we want to expand to outbound edges from found nodes to some destination. But as this is a distributed context, the destination may be either on the machine executing the expand or on some other worker machine. And in such a case, expand will perform communication with other storages if it needs to find the destination node. It would send an RPC and then fetch the node to their own machine and perform additional computation. In our case, the additional stuff to do is a filter, which will just apply the expression. And then we can begin producing the results to the final user, which is done with produce. Now, I said that we have worker machines which store parts of a graph. We also designate one of those machines as a master, which is essentially the same as a worker, stores also parts of a graph, but needs to control the execution and send the results to the client. So produce would just stream to master workers' results, and the master would stream them back to client. So we don't get any accumulation on a single machine. But I'll come back to that later because there are other things we need to do. So can we start planning this? Well, actually, no. We need to do some more additional processing. We would like to extract filters into a regular form. So you may have noticed that we're actually filtering inside the pattern, like captain named Kirk and also a friend of on the edge. But we can also do the same in where, like we did with destination B. So in our case, it doesn't matter how the user writes the query, because we transform this to just regular where separated by AND operations, Boolean. So this would get transformed into A filtered by label captain, and A.name needs to be Kirk. We also do the same for the edge. And we are ready to continue our processing, but why do we actually do this? We want to find out which symbols or variables are used in each expression for filtering, and also detect whether the filters are suitable to be replaced by an index lookup. So if the user has created an index on combination of label and property, then we can remove the filter altogether and replace the scan all with the scan all on the index, not the whole storage. So yeah, this, and we also want to apply filters as soon as possible. So the user can combine multiple variables to form a filter expression, but as soon as we have found the required variable values, we can just put the filter and reduce the number of results immediately. Now we can actually begin planning the match. Well, the user has written this query. It wants to find the source A, traverse outwards to B, and get the results. But that doesn't have to be the way we actually match things in the graph. We can, for example, reverse the order. We can find B and then traverse all inbound edges to get to A. And the alternative also is to find perhaps both A and B, combine them in a Cartesian product, and then just check whether the pairs are connected. Now, all of this has different implications, and we'll come to that a bit later. So let's take a look at our first interesting case, which is just finding the source. So we will plan a scan all operation, pipe that output into a filter based only on A symbols, see if we can maybe replace it with an index. And this usually means where the index exists, and as I said, whether the filter is suitable for that. Afterwards, we just traverse all the outbound edges and filter the results. The other interesting case is a Cartesian product. So we would find all A's. Then we would find whether we can use the index, and also do the same for B. And now these two branches of operations are merged into a Cartesian product, which then performs an expand, just checking whether the pairs are connected. So how do we choose which one is better? Unfortunately, in a general case, we cannot check all of the plans, all of the combinations, and determine the optimal execution. That would take too long time, and perhaps it may not even really be possible if we don't have enough information from the database. So we use a heuristic approach, which is cost estimation. basically, each operator is assigned an estimate of how much results will it produce, or perhaps reduce, like filter. So scan all is expected to produce a lot of results. Index scan will produce less results, and filter will hopefully filter something. And we also want to give each operation the cost of its execution itself. So scan all by index will have to look through a map to get to index and iterate that. So it may be a bit more costly per se against regular scan all, which just starts iterating. It doesn't have to do additional computation maybe. But usually you always want to use the index. So we can continue with that. In our case, we had two interesting plans. The first is scan all by index, expand, and filter. And the implications are, for example, if we have large amounts of edges on each node in a graph, so the average degree is very high, then the first plan will be a bit not as good as the second one, because we will find all nodes and start traversing all of the edges on each node. On the other hand, the second plan would find all nodes, both endpoints, and the edges between them would just have to be checked whether they exist and not traversed. Of course, if the average degree is low, then the first plan is better. Since this is a distributed context, we also need to account distributed execution. So as I said, each worker will store a part of a graph. And we want to make each worker very busy with execution. So we want them to give as much as possible to execute on their own. So for example, with scan all, expand, filter, each worker can produce the whole execution. This means that the worker will find all nodes via an index in its local storage, expand to destinations, and potentially fetch them from other workers, which increases the communication overhead. But the same worker can also perform the filter and then propagate that results to master. So each worker would need to communicate a bit among themselves, but make a lot of work on their own machine. In the other case, we can only perform this part of the query on each worker because Cartesian needs to see all of the results. And the master is designated as the one controlling the execution, and as such will receive the results of each scan all and combine them into a Cartesian product to get whether the pairs are connected or not. Now, this has other implications with regards to communication. So workers will be completely standalone and will not have to communicate among themselves. They will just produce the results back to master. On the other hand, depending on how Cartesian is implemented, the master may need to accumulate the results of one side of a Cartesian pair. And this can increase the memory consumption, especially if we are using a distributed system to store a large graph, which doesn't fit on one machine. So that's the trade-off. And of course, the cost estimation will need to estimate these trade-offs and hopefully choose the better plan. It's not always the case because we need always to tweak it, and basically there are a lot of papers written on how to choose and find the appropriate solution. In our case, we will take the simpler plan, which is find Captain Kirk by index and expand to destination, apply filters, and produce the results. Traditionally, this is written reversed, so produce is at the top. The reason for this is because we want to get the results of the final operation, which is produce, and all of the rest operations just serve as the input to get that result. Additionally, as I stated before, this whole operation plan will be executed on each storage worker machine and just streamed through master to client. There will be no memory accumulation. So the question is, how do we actually execute it? At Memgraph, we use a pull mechanism, which is essentially an iteration, like done in a for loop with iterators or similar. So for each operator, we produce a cursor data type, which is an iterator, basically. So at the top of our plan, we have produce. We call make cursor on that. It gives us a cursor, but recursively constructs all the cursors of all the below operations. Then we can call pool on set cursor to get one result. And that pool will also need to call other cursors to fetch the input, make a computation, and get what we desire. Now, this is really good because it's essentially lazy evaluation, so we will save a bit of memory. And like in functional languages, limiting and skipping becomes very natural. You just pull as many times as you want to get the number of limited results. Or maybe you just want to skip some results, so you pull that, discard it, and continue regularly afterwards. But unfortunately, there are some operations which aren't as nice to this approach. So for example, ordering results needs to know the whole data set in order to sort it. Now, in a distributed context, of course, each worker can sort their own results. So the master will need to only have the last result of each worker. Since it knows it's sorted, it can produce the results without actually consuming as much memory. But workers may still get bloated with memory usage if the user is trying to sort like the whole local storage. And also, CRUD operations are a bit of a problem. Unfortunately, in OpenCipher, we can do both write and read queries at the same time. And this forces us to perform all of the CRUD operations, accumulate the results, and have a synchronization point for all the machines. And afterwards, we can produce the results in the order they were given, which is rather unfortunate for distributed execution. Hopefully, the users don't use as much CRUD operations in regular usage. So let's take a look at how execution will be done on our example. We have our query from the start. And we have the chosen plan. So as I said, this is done on each worker. But since our graph in example is very small, basically only one worker will have something to do, since Captain Kirk cannot be at two places at the same time. So let's start off. We call pool on produce, which needs to get the results from filter, which in turn needs to get the results from expand, and then lastly from scan by index. So scan by index, we look into local index storage, find Kirk, and set the value on the frame. Next up is expand, which will traverse one of the edges for starters. Now, Spock may be on another machine, so maybe this will be fetched from the other worker. Maybe it's local, we don't really care. And it will put both the edge and the destination on the frame. When we have that, we can filter B, which is essentially just checking whether the Spock is an officer. He is. So filter will propagate the result back to produce, which will transform B as b.name to get just the value of the property. This is then sent to master, which just streams it back to client. Next, we call another pool. So produce will go down to filter and back to expand. Now expand will not call scan by index because it hasn't traversed all of the edges yet. So for example, here we go to McCoy. And now the filter actually has some job to do. McCoy is a doctor and not an officer, so it will get filtered out. What this means is that filter will not propagate the result to produce. It will just call for the next result from expand. And expand will go to Uhura and send that back to filter. And filter is satisfied with that. So it sends it to produce, which in turn streams across the master to client the result name Uhura. And the final pool is going back to scan by index because expand has traversed all of the friend of edges. And scan by index cannot find another Captain Kirk. This is just a single timeline, no time traveling shenanigans. And this essentially completes our execution. The client is sent, these are the results, you receive them all, and we are good to go. So the next example is the one that doesn't really work nicely with distributed execution, and these are Crud operations. So here we'll have a match which finds all officers, and on each officer we would like to set a new property, arrogant to true. And afterwards we would like to return only one officer. What this implies is that all officers will have the property set, but only one will be returned as a result. For that, I don't know if you can see this very well, because the plan is now split. So we have the worker part, which finds all officers by index and sets the property on them. After it does that, it sends the found officer to master machine, which needs to accumulate the results of all worker storages, and then set the synchronization point after it received all of the results, and then begin producing the originally received results back to produce and limit and back to client. So in this case, we could accumulate large amounts of memory. The frame for this execution is very simple. So we only have one variable a. Technically, we have another one for return, but to keep it simple, we treat it as the same here. So let's start execution. So, for example, one worker could find Spock, sets the value on the frame, then sets property on it, and sends it to master. Afterwards, master needs to receive more data. So perhaps another machine would find Uhura, set the property on it, and send it back to master. And I believe these are all the officers in this small example. So the master can begin producing the results as it received them. In this case, Spock was the first one, so it will set Spock on the frame like nothing happened in between. The produce doesn't really have to do much in this case. We only have to limit the results. Since this is the first result, we just produce it back to the user. And then another pool on limit will say, oh, I'm done. We only want to limit one result. So we are back to the end. Anyways, thank you for attention. I hope the examples were clear. Also, we can start with the QA a bit. I left plenty more time so that you can ask me a lot of questions. I know how many of you are actually involved with graph databases, and of course, we are hiring. Thank you.
Okay, you showed some kind of simple queries where you had two nodes and an edge connecting to them, between them. How well does the system work if you, for example, ask for, let's say, a cycle of 4 nodes that each connect to each other? Because I could imagine that potentially you have some recursion going on there. Like, how does the system deal with that?
Yeah, well, in case of a cycle, well, basically it depends on how long the cycle is. We could either have plenty of communication between worker machines if we just take the source and try to expand back to the source. Another case is to have different points of sources at the same time. So we may start from both sides of our cycle. So we basically take one node and go in both directions at the same time. This could be done in parallel, but we also need to have like a merge point which checks whether we've found the middle connection. The system currently deals with that just for cycles of length 4, as you said. It's very simple. You just traverse the edges and check whether the destination is the same as the source. If it's not, if you don't find it, then you just break the loop early. I hope that answers the question.
All right. Any question?
Hi.
Hi, thank you for your talk. In your cost model, do you use any estimates or statistics in each worker that could help estimate the subparts of the query?
Not yet, unfortunately. This is all still a work in progress, but yes, that is the plan. We have an overview of like indexes created and how much nodes are stored in the index, but we also need additional information like average degree, and that hasn't been yet implemented. But yeah, good question.
Okay, we got another question. All right. Looks like we finished early. Thank you very much, Tom.
Thank you.